let's start this up here. We're recording. I'm not on mute. Good. I feel like I have to say that every time now. Just make sure I'm not on mute. We'll call it interpretive math. Just happens on the screen. So, oh, was I even in the right little section here? I was not. So we're going to finish chapter 2 today. And then we've got our test on Tuesday, right? And so make sure that you do these practice problems, right? But, and there are a lot of problems. Squeeze them onto 4 pages, right? But just make sure that you're able to do all of them. And if you have any problems or questions about the problems rather, then ask me, okay? Because if there's one of these on here that you don't know how to do, you don't just want to hope it's not the one that's on the test. Let's kind of tackle it. Oh, one thing. So if there's extra information, so usually it just says 6 of the following, 2 of the following. But then for section 2.3, it says you'll be given the graph on the test, right? So when you're working through these problems, you can just use Desmos to graph it, right? And then pretend that you have the graph, right? Because you have that tool. So you're able to graph it, look at the graph, and then answer the problem, right? Answer those questions. So you'll be given the graph on the test, so it'll be okay. Same thing with 2.5, right? You're gonna have to draw a straight line essentially, right? And so, and we'll give you an empty plot to put it on, right? So with the axes already on it. But here, when you're working through all these, right, I can't give you 19 to 26. 26 minus 19, is that, I don't know, 7? I'm not going to give you 7 empty plots, right? You have to make them yourself, but on the test, it'll be easier because I'll just give it to you. Right? And then finally, for section 2.8, which we're going to talk about today, right? So it'll make more sense after today. But in addition to finding the inverse, you're going to show that it's 1-to-1. And there's going to be one of these problems on there. Yeah. So, test number 1 on Tuesday. Okay. Practice test solutions will be posted as soon as I can over the weekend sometime. So that's all I'm committing to over the weekend. And then no class on Friday next week, right? We're saying early reading break. So no class on Friday next week. Okay. All right, because we had a little bit of wiggle room, so may as well use it. Okay. Does everyone have the? I've got a lot of chapter 2 notes though. Does everyone have chapter 2 notes? 2.5 to 2.8. That used to be the worst in the class. Everyone else has the chapter 2 notes, I think, right? Phew. Well, there's only 3 left. 3 people that aren't coming. Actually, I think I printed less than I needed even. So, okay. So we're gonna do 2.7, which is on combining functions. So we've been talking about functions. Oh, and another thing, the chapter 2 quizzes, I can tell that you're working on them, right? And so that's really good because I did make them due on Tuesday, right, at midnight, mostly so that you use them to practice for the test, and then we can kind of be really free for the reading break, right? And so they are nice and short though, so I mean, hopefully you've started on some of these already. So 2.7 and 2.8, that's all we've got left in chapter 2. So 2.7 is on combining functions, and I'll just pull in that blurb right away here. So here, copy. One that you have. So if we've got a function f and a function g, what we can do is we can combine those functions and have a new function called f plus g or f minus g, or even f times g or f divided by g, right? And so we can add or subtract or multiply or divide functions to create new functions. So usually we're concerned with the domain, but what happens is if we have the function f plus a g, right, that's going to make a new function. And so if we have f plus g of x, what we can do is we can just add those two functions together, right? Add them together, smush them together, and then simplify, and then we have a new function, right? And so we just take f of x plus g of x is the same as f plus g of x. Okay. Same thing with the subtraction, we can just split the two up and subtract f of x minus g of x. Multiplication, same thing, right? It behaves the same thing. So if I want f times g of x, I just take f of x times g of x. Division, same deal. Right? Notice over here the domain. The domain, remember, is all the possible values of x. Okay, so here, the domain is all possible values of x. So if we say that f has domain A and g has domain B, right, they're not necessarily the same, right? Then if f has the domain of all real numbers, for example, and g has the domain from 0 up to positive infinity, right? Then when I'm adding these two functions, well, f can take on any number, but g has to be positive. Well, adding these two together, right, I have to satisfy both the domains. And so now my overall domain is going to be just where they overlap, which is where all the positive numbers are, right? And so here, the domain of the new function is the overlap of the two, I'll put old in quotes, of the two old functions. The only new thing is when we're dividing, right? So we've got f over g of x or f of x over g of x, they're the same thing. Now we can't divide by 0, right? So on top of the shared domain, right, A and B, we write this so such that g of x does not equal 0, right? Because we can't divide by 0. So what we're saying here is that we can't divide by 0. So we've got that added condition. So wherever g of x is 0, we have to pull that out of our domain as well. So how about we do some examples here? Oh. I actually wanted to do maybe, but they, I guess, they're different. Kind of a bigger problem here. How can I squeeze these on the same page? There. So what we're going to do, we're given f of x and g of x in each of these problems, right? And then we're going to find f plus g, f minus g, f times g, and f divided by g, as well as their domains, right? So what I want to do is I want to have do a little bit of a trickier one. Let's do 16. Sold. So 16, just writing it out, f of x is 2 over x minus, or x plus 1. And g of x is x over x plus 1. First thing I'm going to do is I'm going to figure out my domain of f and my domain of g, right? And so let A be the domain of f of x. Then A, and I'll use interval notation, right? Because that's kind of it's the easier one. Like set notation is a little bit trickier, right? So on the test, I'll be asking for interval notation, if anything. And so the domain of f of x, well, the only hiccup here, remember, is that we're dividing. So whatever we're dividing by just can't be 0, which means that x plus 1 can't be 0, right? Which means that x can't be -1, right? And so what we have is we have this from -∞ up to -1 not inclusive, right? Union, right? Combined with, and then starting back up at -1 and then up to infinity. Those round brackets say, hey, we can be everything except for at -1. Everything else will yield real numbers. And so B, let that be the domain of g of x. Looking at g of x, to me, that looks like it has the same domain, right? Because we're dividing by x plus 1 again, right? And so here, B is going to also be from -∞ to -1, round bracket -1 to infinity. That's nice, right? That we've got the same domain, because now A and B, there's going to be no points that get taken out. But I'm going to clarify, I know too little too late. X plus 1 equals 0, or else it can't equal 0, so x can't be -1. Just to clarify in case that wasn't clear. Right? But we have done domains before, right? So we're just kind of moving it along. Not too many. I said they'd come back and then come back and then come back again. So here they're back again. All right. So now, if we have to find, because we know that the domains of f plus g, f minus g, and f times g is just going to be A and B, right? And so we can find A and B. I can't remember if I told you guys when we've got this kind of cap, it's called, it's a cup and a cap. The union, the intersection. The union I read as or, and the intersection I read as and, right? So A and B. But whichever term you want to use is fine, but sometimes it's easier to visualize if you read it as and.
So the intersection is where they both share the same.
Exactly.
And
the union
is everything.
Is just
what they
this or this,
yeah.
right? And so that's why I find it's easier if we just read this as or, because it can be from -infinity to -1, or from -1 to infinity, doesn't matter, right? Cool. So A and B, if these were different, it might be easier to just plot little number lines, right? And see where the overlap is. And then it'll be easier to visualize, okay, it's this section here that I've got this overlap. We can see that it's just going to be the same as what they both are, right? So A and B is from -infinity to -1, union -1 to +infinity. So I'll leave it at that, and then once we have a look at f of x over g of x, then we can deal with that specific domain. And so this will be the domain of f plus g, f minus g, and f times g. So now we're just going to go ahead and find these things. F plus g of x. Yep.
Why is it not the domain of f over g as well?
It is, but f over g is going to have this, but with the added condition that g can't be 0, right? Because now we're dividing by g. So I'm going to leave it. It is definitely part of the domain of g, except or f of g over g, but we've got that added. Yeah. Cool. So from that little blue box, right, we know that we can rewrite this as f of x plus g of x. Now we can just plug in our functions, which were 2 over x plus 1 plus x over x plus 1 Nice. I've got a common denominator. Don't need to deal with that. Right. So now I've got 2 plus x over x plus 1. And I'm not going to I'm not going to put in any work. This is fine. Right. I'm sure I could rearrange this some weird way and pull out something, but nah. Right. Once you're here, good. How about f minus g of x? Again, we know that we can rewrite it as f of x minus g of x, which is, again, 2 over x plus 1 minus x over x plus 1. Same thing here, common denominator. So I'm safe. So I have 2 minus x over x plus 1. Same thing, just going to leave it. F times g of x is f of x times g of x. A little bit sneakier, right? It's going to get a little bit bigger here. F of x was 2 over x plus 1. G of x, so times x over x plus 1. I'm going to use the fact that I've got that common denominator and just rewrite it as a squared. If you wanted to expand it, that's fine too, right? Because if we're multiplying fractions, then we just multiply across, right? So then we get 2x over x plus 1 squared. But I'm just going to leave it there. Notice here, right, for all of these, over x plus 1, over x plus 1, over x plus 1 squared, the domain is just consistently, well, x can't be -1. So now, if we have a look at f over g of x, that's f of x over g of x. Which is going to be a fraction over a fraction, right? 2 over x plus 1 divided by x over x plus 1. Fraction over a fraction, right? I have to flip it, multiply it. So now I get 2 over x plus 1 times x plus 1 over x. Remember that I'm treating these as one thing, which means I can cancel them, right, to simplify things. So I can get rid of this, and so I just get 2 over x. Here's where we have to be really careful, because if we only looked here, right, we would say, oh, well, x just can't be 0, right? But because we got them from 2 other functions, right, we have to make sure that g of x as a total thing doesn't equal 0, right? And so that's where this added. So for the domain of f over g of x, we need to make sure g of x does not equal 0, right? Any values that are going to make the entire g of x 0, we have to pull out. Okay? So the domain it's going to be that overlap, right? Is going to be A and B. Not as well. Excluding values that make g of x equal to 0. That'll be easier to. Okay. Which means we have to figure out, well, when is g of x equal to 0? So g of x is equal to 0. G of x was x over x plus 1. G of x is going to be 0. The only time that g of x is going to be 0 is if x is 0. So it worked out to be the same thing as before. That's not always the case though, right? And so that's why we have to look at, okay, well, g of x, because there's nothing I can do down here because I can't divide by 0. It doesn't give me a number, right? And so there's nothing that I can do down here to get me to 0, right? The only way that I can get to 0 here is if this top x is 0, right? And so
x can't be 0 and x also.
That's right. Yeah.
But for the denominator, you just look at if it's a fraction, you just put the top. What would make it 0?
Yeah, so here, so technically what we could do is we could say, okay, well, to solve this, right, I could say x is equal to 0 times x plus 1, right? I could move that over there. That I'm allowed to do. So then x is 0, makes it 0. Right. But you also want to convince yourself, right, that that x equals 0 is the only option. Right? And so here, that's what I wanted to put. The only value that will make g of x equal to 0 is x equal to 0, right? Because if we plug in x equal to 0, we get 0 divided by 0 plus 1. 0 divided by 1 we're allowed to do. Right? And then, of course, we can't have -1, but we already took care of that because the domain is already excluding -1, right? And now we're adding on another condition. Right? So now we're saying, so therefore, x can't be 0. So the total domain of f over g is from -∞ up to -1, picking right back up at -1, but only going to 0, right? Because then we have to stop at 0. But then picking up at 0 again, going to infinity. So that's the only tricky one is when we've got, so if we're adding, subtracting, multiplying, it's just the overlap of the domain, right? If we're dividing, then it's the overlap of the domain as well as g can't be 0, right? Whatever function you're dividing by can't be 0. So.
And if that function is a fraction, you just have to figure out what would make the numerator.
Yes. Yeah. Sorry, I think that's what you were asking before, and I like, yeah, it's 0. No. Yes. Exactly. Good. Okay. Cool. Let's see. 17 to 20 just ask you to find the domain. I actually want to get into the composition of functions because it's the next step of adding, subtracting, multiplying, dividing functions is putting a function inside a function. And so that's where I want to get to now. So what we're doing here is we're putting a function inside a function. So what we say is if we've got f and then an open circle g of x, how you read this is f composed with g of x. Or sometimes I get lazy and I just read that open circle as of f of g of x, because what we're doing is we say that, well, we can rewrite this as f of g of x, right? Put g of x into f of x. f of g of x. So however you want to read these, it's fine. I actually like this way better. It makes more sense to me instead of saying f composed with g of x. Right, that gets wordy. And especially because this is probably how you'll want to set it up when you're calculating these things. And so you're going to have two functions. And to find f of g of x, you're going to put g of x wherever you see an x in f of x, which we already did, right? When we looked at, so if f of a plus h, right? I guess I should say if we have f of a plus h, which we have been seeing, right? Then let g of x be a plus h and f of x be x, then f of g of x is going to be f of a plus h, right? So put in g of x into your f of x, and then whatever f is, right? Here it's just x, or whatever function you had before, right? Let's let it be x squared minus x. Take it up a notch. F of a plus h then is going to be a plus h squared minus a plus h. Because wherever I see an x in f, I'm going to plug in whatever's inside here, which is g of x in this case. Huh? Pretty sure. Oh, we do find the domains. Rats. Okay. I guess I've got it here. So if we have f composed with g, we need f of x and we need g of x. Of course, we can do it with more than two functions, but I put those as optional, right? When we've got 3, could do 4, 5, 6, whatever, they get huge, right? We're just gonna stick to 2. And so f of x and g of x, oh, question.
Are we supposed to go in this big optional box?
Oh, it's just me breaking it up, right? So everything below it is optional. Yeah, because I wanted to kind of squeeze it on one page, but also separate them. So I made my box bigger, that's all. Yeah, it's all optional from there on out. Yeah, cool. Okay. How about we find a composition first and then look at the domain? Because what happens is, so f has a domain, right? G has a domain, but then I'm plugging G into f. And so G has to satisfy the domain of f. Right? So first let's do one and have a look at the domain after. A little bit opposite of what we just did. Copy. And I'm pretty sure I only copied to 58 because that's how it was set up, I guess, but that's okay. Scoot this over so I can fit it on the same page. Come on. Let's do 52. Yeah, because let's do 52 and 58, how about? Maybe something like that. So 52 says that f of x is x squared, and g of x is the root of x minus 3. We're going to find f composed with g composed with f. What we'll find is that these two things are often not the same thing, right? Usually not the same thing. These are usually different functions. F composed with f, and then g composed with g. Oops. Okay. Let's start with f composed with g. F composed with g of x. If you want to just write it or start with f of x or f of g of x, that's fine by me. Right. Because even just knowing that they're the same, that's good. So if you want to just start at f of g of x because it makes more sense, then that's great. So what I do is I hold this x steady for the first step, and I just take my g of x and I plug it in here. Right, so I start from the inside and work my way up. Of course, you could do the other way around, right? I'll show you both the first way, but for me, I like working from the inside and then working my way out. Okay. So we could say that this is the same as f of g of x, which is root x minus 3. Or f of g of x is going to be x squared, but wherever I have an x, it's going to be g of x squared, right? Because f is x squared, and so I've got g of x squared. Right. I prefer this method. But just so you know that you're not wrong if you want to use this method, right, where you want to work from the outside in, right, wherever you see an x in f of x, you're going to replace it with g of x temporarily and then plug in g of x, because what you'll see is you end up at the same thing. So here, f of root x minus 3, well, f is just x squared, so wherever I see an x, I'm going to do root x minus 3 squared. Same thing over here. I replaced g of x with its actual function, which is root x minus 3. Root x minus 3 squared. Right. So you end up in the same spot, of course. It's just a matter of where you want to start from. Okay. But like I said, I usually like this method because, I don't know, this method for me requires more thinking, right? Which I don't like. So I'll probably use that method. Just know that you're right either way, right? We end up at the same spot. Okay, so now I can, usually we have to expand and simplify, right? And so now if I just keep working on this darker one, then I have x minus 3, so the root of x minus 3, but then I'm squaring it, and so now I'm just left with x minus 3. Yeah. So here, now if we talk about the domain, right? F has a domain, right? In this case, the domain of F is all real numbers. Right? So x squared can take any value of x and it can handle it, it's fine. G of x though, right? We can't have any, so x minus 3 has to be greater than or equal to 0. And so, but I'm plugging in g of x into f of x. And so my domain, I think there's a little, this is the little kidney bean image on your handout. I'll put it in here. Okay. So what we're saying here is that the domain, so I'll just kind of underline here. This is saying the domain of f composed with g of x is the overlap of the domain of g of x is the overlap of the domain of g of x and the values of g of x that satisfy the domain of f. And the values of g of x that satisfy the domain of f. So we have to make sure that whatever we're plugging in has to satisfy G, right? And then if there are restrictions on the domain of F, then our G has to satisfy those restrictions because we're plugging it into F. Right? And so if we have a look at, so our F of X, just to have it on the same page here, was X squared, and G of X was the root of X minus 3, I want to say. The domain of f of x is just all real numbers, right? So in interval notation, that's negative infinity to infinity. X squared can handle any value of x. G of x, not so much. The domain of g of x, well, I know that x minus 3 has to be, and it depends on if you want to figure out which ones they can't be or can be. It doesn't, sometimes I switch it up, right, depending on what makes more sense in the situation. But either way, you'll get to the same answer. So x minus 3 has to be greater than or equal to 0. I can add 3 to both sides, right, because we know how to work with inequalities. And so I have to say, so x must be greater than or equal to 3. It's allowed to be 3, but it has to be 3 or bigger. So the domain of g of x is a square bracket from 3 up to infinity. So if we're thinking, so we have to start from the center, right? G of x, the domain of g of x has to be satisfied. So that domain is here. So already we've narrowed it down to just x's from 3 to infinity, right? Inclusive. Then I'm plugging it into f of x. And in this case, there's no restrictions here, right? And so fine, then the overlap here is just this little guy, right? So the domain of f of g of x is going to be 3 inclusive to infinity. So therefore, the domain of f composed with g of x is from 3 to infinity. Huh? Which I can't remember what our, yeah, here's our new function, right? There's no way that we would get that domain from here, because from here, well, x can be any number, right? But we have to remember that it came from 2 other functions that have their own domains, right? And so just looking here isn't going to do it, right? You have to look at the domain of g of x, right? It has to be satisfied before it can get plugged in here, but then it also has to get satisfied in f, right? Or it has to satisfy f. So let's have a look at g of f then. And what we'll see is we'll probably get very different functions. So if we find g composed with f of x, or if you prefer g of f of x, out of curiosity, I know you haven't tried a lot of these or probably any of these, would you prefer this method or this method? First one? Yeah, me too. I don't know why, but for me, it just makes more sense to work my way out. Okay, so are you okay if I just do this one then? Cool. Let's do it. So starting from the middle, f of x is still x squared. So now I'm finding g of x squared. G is the root of x minus 3. So wherever I see an x, I'm going to replace it with x squared in this case. And so I've got the root of x squared minus 3. Okay. All right. So I'm going to leave it like that. I don't see any obvious way that I could kind of get rid of that square root, and that's okay. Right? Now to find the domain, right? We've got f, which can take any real numbers, right? But g has to have x minus 3 greater than 0. Right? And the x that we're plugging in is x squared minus 3. Yeah. What I find is I have to break it up, right? So here's our domain work. The domain of f is from negative infinity, to infinity. That's fine. Okay. But then the domain of g of f of x is that f of x has to be greater than or equal to 3. Right. That's the same thing, but now because our g of x is actually taking f of x, right? Our f of x has to be greater than or equal to 3 to satisfy the domain of g. So f of x is x squared has to be greater than or equal to 3. And so x squared plus or minus root 3. Oh, dang it. It's one of those hard ones, right? The square root inequality. Usually I just end up figuring out test points. where it's greater than or equal to 3 or 0. Because see the problem here. Here I am at negative root 3. Once I square it, right, root 3, negative root 3 becomes just 3. Root 3 becomes just 3. So either way, they'll both work, right? But here I'm at negative root 3 and root 3. If I plug this into just boil it down to x squared is greater than or equal to 3. If this is my x, so if negative root 3, negative root 4 as my test point, is going to be negative root 4 squared. Is it greater than or equal to 3? It is, right? Because 4 is greater than or equal to 3. So that one's good, right? Which means between here, between negative root 3 and root 3, I'm going to pick a convenient value of 0. Is 0 squared greater than or equal to 3? No, it's not. And then same idea here. I'm going to pick positive root root 3 root 4. Yeah. Okay, still works. Root 4. I just wanted to make sure that my roots were actually behaving the way I thought they did. Root 4 squared, is it greater than or equal to 3? 4 is greater than or equal to 3. The tricky part is because we've got that square in there. Okay, so if we had to write this out in interval notation, right? In interval notation, we get from negative infinity up to and including negative root 3. And then empty, empty, empty up until positive root 3. Oh, and including square bracket up to infinity. Okay. So this is going to be where g of x is the domain of g is satisfied by x, right? Or f of x, sorry. So f of x is fine. We can plug in anything into g, right? Or we can use anything for f and f will behave fine. That's not the hiccup. The hiccup is the g, right, can only handle certain inputs of f, right? And so we're forcing f of x to be greater than or equal to 3, right, to satisfy the domain of g. And so then whenever you get something like this, it gets kind of nasty. And for me, in my head, it doesn't really work out. And so that's when I just resort to drawing a number line with some test points just to see where it's actually behaving the way I want it to. And then I can land on this interval here. So because there were no restrictions on what I can plug into f, right? The domain of g of f is going to be this one. So since there were no restrictions on f of x, the domain of g composed with f of x is negative infinity to negative root 3 square bracket union square bracket root 3 positive infinity. If there were restrictions on f, you'd have to take the overlap of the two. Yeah. And I'm just going to flip forward because I do want to talk about 2.8 as well, of course. Do you want to use a different function maybe? So we don't only know these two functions? Because we were supposed to go through, of course, the question asks for, okay, do all these. Find f of g, g of f, we did those. You can find f of f, g of g, but how about we do the 58, those two functions, and let's just have a look at f of g, for example, right? Before we keep going. So 58, just put it on the same page here, 58. Let's just find f of g of x. Uh, 58. Hey, what? I don't have 58 on here. I stopped it at 57. Secret. I'm like, 58 is going to be so important to you guys. No. Here, I'll just, because you guys have till 57, yeah. How about that? Yeah, let's do 57 then. '57 says that f of x is x over x plus 1. Hey, looks familiar. And g of x is 1 over x. Huh? First off, let's establish what the domains of all these are, right? Because now we will deal with the function composition, but let's tackle the domains. So the domains the domain of f is, well, we already talked about this one, right? X can't be -1. And so X can't be -1. And the domain of G the only restriction here, I've got 1 over X, so X can't be 0. We can definitely write these in interval notation, right? But I'm just going to leave it because what we have to do is we have to combine these. And so if we're finding f of g, f of g of x, the restriction on g stays the same, right? So x can't be 0. Right? Otherwise G wouldn't exist and we can't put it in. Fine. But now, just gonna rewrite that out, f of g of x. Right? I'm still talking about the domain though for now. X can't be 0, right? But then for the domain of f of g of x, well, the domain of f says that x can't be -1, right? But now I'm using g of x instead of x. And so here I'm saying that g of x can't be -1. So the overlap of these two, that's going to be my domain. Right? And so the overlap of these will be the domain. Right? We just have to find where g of x is not equal to -1. So if g of x can't be -1, well, g of x is 1 over x. So I can replace that 1 over x can't be -1. Even though I've got that not equal to, right? I can still treat it like an equal sign. And so I can multiply both sides by x to move it over. So then 1 can't be -x. -1 times x, but then x can't be -1, which makes sense, right? Because 1 over x, if x is -1, then I get 1 over -1, which is -1, which we can't have, right? So you always want to just talk yourself into what you're saying, right? And say, okay, oh yeah, that makes sense. So then x can't be -1. And I always, usually as soon as I can, I switch it over so that my x is on the left-hand side, but don't have to. So now, right, x can't be -1. All right. So therefore, the domain of f composed with g of x is that x can't be 0 and x can't be -1. Anything else goes, right? So in interval notation, we would go from -infinity up to -1, not including -1, picking up at -1, going to 0, picking up at 0 again, and then to infinity. Oh, this u looks a lot like a 0. Whee! Oh. Good, we've got the domain under control. Now, if we just have to find it, f composed with g of x, it's the same as f of g of x. I'm going to start by replacing my g of x. G of x was 1 over x, so I want f of 1 over x. Wherever I see an x in f of x, I'm going to replace it with 1 over x. And my f was x over x plus 1, so I get 1 over x over 1 over x plus 1. I have to get common denominators, and then I've got a fraction over a fraction, right? But from here on out, we know what we're doing. So we've got 1 over x over 1 over x plus x over x, right? Kind of fast tracking, finding my common denominator, right? Because 1 is just 1 over 1, but I want it over x so that I can add these fractions. I took 1 times x over x.
Did you take 1 over x plus 1?
Is that not what I'm supposed to be doing? Yeah,
So
1 over
x plus 1 equal to
right here.
Yeah.
Yeah. So here, wherever I see an x, because f of x, let me just make sure that I did it right. F of x is x over x plus 1. So to do f of 1 over x, wherever I see an x here, I'm going to replace it with 1 over x. 1 over x over 1 over x plus 1. But then to add these, I need to get this over x. Right? And so what I do, my trick, is I multiply this 1 by x over x. And then I get x, because it's just times 1, right? X over x. And now I've got a common denominator. So now I can add them. So now I've got 1 over x is just staying put for a little bit longer, and then over 1 plus x over x. Fraction over fraction, I flip, multiply, and so I get 1 over x times x over 1 plus x. Good thing these x's cancel. And I'm just left with 1 over 1 plus x. So again, if we have a look at the domain, we said, well, x can't be 0 and x can't be -1. If we had looked at just the final results here, yeah, we can all agree that x can't be -1, right? But we would have never guessed that x can't be 0, right? And so that's why we have to start at the top and figure out what those individual domains are, because we can't rely on just the final answer. Cool. So, any questions? No?
Could you do like an F of F?
Mm-hmm. Let's do f of f here. Actually, which one's going to be harder? F of f is definitely going to be harder. So let's do that one. F of x is f of x. And I had it here, but remember that f of x was x over x plus 1. So I'm keeping the f on the outside. Right? Do you guys want to find the domain first, or do you want to solve for the function first? It doesn't matter. Right?
Domain first.
Domain first. Do the hard part first. Sounds good. So here, focus on this little guy here, f of x. Well, we know that x just can't be -1. Right? Out here, we said, well, what I'm putting in here can't be -1 either, right? And so now we're saying that f of x can't be -1. So now we just have to solve where f of x equals -1 to pull it out of the domain, right? Or all the values where it's equal or not equal to -1, either way, right? Just remember if you're pulling things out or putting them in. So if f of x equals -1, because sometimes, right, to figure out which values we need to pull out of the domain, right? So to figure out which values we need to pull out, right? Or if you did something like f of x can't be equal to -1. I guess it does the same thing. When you put it on paper, in my mind, they do two different things. We don't need to write that, I guess. Either way. Or do this. About that. So if we're saying, well, f of x can't be -1, maybe let's stick to that because that's what we used last time. Nice to be consistent, maybe. Well, sometimes I mix it up. So if f of x can't be -1, f of x is x over x plus 1. And we're saying, well, it can't be equal to -1. Same idea, right? I can use this not equal to as an equal sign, and so I can move things around and say that x can't be equal to -1 times x plus 1. So x can't be equal to -x minus 1. Solving for x, right? I can move this -x over to the left-hand side, so I get x plus x can't be equal to -1. So 2x can't be equal to -1. So x cannot be equal to -1/2. Didn't see that coming. Right? But you can try it out, right? If you have x is -1/2, you get -1/2 over -1/2 plus 1 makes -1. So x can't be -1/2. Yeah. So therefore, the domain of this guy, and even if you want to say, okay, well, this actually translates to x can't be -1, that's a good idea. This translates to x can't be -1/2. Because now it's this overlap that we have to take care of. All other values seem to be fine. And so we can't have -1/2 and we can't have -1. Therefore, the domain of f of x is from -∞ up to -1, not including -1. So none of these are inclusive, right? So we've got round brackets all around. -1 to -1/2, and then -1/2. Oops. To positive infinity. Now, f composed with f of x is f of x. Now we can just find it. F of x is x over x plus 1. So we've got f of, and I'll do a big bracket here, f of x over x plus 1. In f, right, you just have to put your blinders on and just treat this as one thing, right? And it will get kind of big, right? And so wherever I see an x, I'm going to plug in x over x plus 1. And so I get x over x plus 1. And I'll put brackets around it just to emphasize that it's just working as one thing, over x plus 1 plus 1. Again, I need a common denominator. I have x over x plus 1 all over x over x plus 1. I'm going to cheat and just do the common denominator of x plus 1 over x plus 1. This puts me at x over x plus 1 over x plus 1 over x plus 1. Gonna do a little magic, right? X plus 1, I'm gonna combine that to make 2x plus 1, but also in the same step, I'm gonna flip and multiply. If you wanna break it up into 2 steps, that's great. But I'm gonna do x over x plus 1 times x plus 1 over 2x plus 1. The x plus 1s will cancel. And so we get, oops, x over 2x plus 1. We did it. Nice. Okay. Oof. You guys ready for a marathon in 2.8? As if this wasn't bad enough. No. So 2.8 talks about inverse functions, but it starts with talking about one-to-one functions. One-to-one functions just say that each x maps to its own value of y, right? So they're not mapping to the same value of y anymore. They're mapping to, so one-to-one. So one x goes to one y, one x goes to one y, right? And so, and the reason we care about that is because in order to be invertible, meaning that we can reverse it to kind of get back to where we started, it has to be one-to-one. Okay? And so section 2.8 is one-to-one functions and their inverse or inverses. A function is invertible. A function is invertible if it is one-to-one. So we need to know how to do two things, right? First, I need to be able to check to make sure and argue that a function is one-to-one. And then I need to be able to find the inverse of it. But the inverse is, so if you've got something like, now I can't even think of one. So say, or let's pick, you know what? Let's not go there. Let's just talk about if it's one-to-one. Okay? Because this is the key. So a function is invertible if it's one-to-one. The inverse of a function is what undoes it, right? To get you back to x, right? And so if you've done, okay, here we go, x minus 3 all squared, right? To undo that, to get back to x, right? Then you would have to take the square root plus 3, right? To get back to x. And so the root of x plus 3 would be the inverse. But we'll get there. The notes use f of x1 cannot be equal to f of x2. I'm going to replace those with a and b. And so what I'm going to say is that a function is one-to-one if we can show that f of a equal to f of b means that a equals b. Okay. So for example, 2.8 notes. if I steal these here. If I have a look at something kind of on the simpler side, if I have a look at 14, for example, f of x is 3x minus 2. If I want to show that this is invertible, or if it's 1-to-1, those two are the same, right? But for now, we're just calling it 1-to-1. What I'm going to do is I'm going to have f of a equal to f of b, right? F of a is just, this is way easier than what we were just doing, right? We just plug in a wherever we see an x, so 3x minus 2, and then f of b, I use 3b minus 2. So you're going to set it up like this, and then you're going to work through it. Oh, I didn't use a, did I? 3a minus 2. I'm going to move things around, simplify, simplify, and at the end, if I end up at a equals b, it is 1-to-1. Okay? And so here, right, I can add 2 to both sides. It doesn't matter which way you're moving, because what you get is 3a minus 2 plus 2 is 3b. But these will cancel. So 3a equals 3b. Divide both sides by 3. Doesn't matter which way you're moving, right? So if we have a over 3b over 3, a equals b. So since we were able to show f of a equals f of b means a must be equal to b, we conclude that f of x is 1-to-1. Or we can conclude f of x is 1-to-1. Let's do one that's maybe not invertible. Let's do, I don't know. Let's do 17. We've got h of x is x squared minus 2x. What do I know about even powers of x, right? X squared, x to the 4th, x to the 6th. I know they look like a parabola, right? This value of x and this value of x both yield the same value of y, not 1-to-1. Right? So that's why I picked this one, because I know it's not going to work out, right? But what I'm going to do is I'm going to set h of a, is it equal to, or I'm going to force it to be h of b, and then I'm going to land at if that means that a equals b. So I get a squared minus 2a is equal to b squared minus 2b. I think what I'll do is, I don't know how to get out of this mess. I know it's not 1-to-1. How am I going to show it? I think what I'll do is I'm going to solve for a squared or b squared and try to kind of isolate them. Or I guess another thing I could do is I could pull out a common a, for example, on the left-hand side. Let's try that. A times A minus 2. It's not going to work, right? And so if it is 1-to-1, it'll just fall out, right? Which is actually hard to think about, because when we did this and saw this, it's like, well, yeah, because I put them in there, right? But then we see stuff like this, and you're like, well, how am I supposed to solve for one? Never mind making it look like the other thing, right? And so here, I'd probably just say, nope, not 1-to-1. Yeah, what else could we do? I don't know. What can we do here? B times B minus 2 doesn't really do anything. Not 1-to-1. How about that? Right. Because you don't end up at A equals B easily, it's not 1-to-1. Right. And especially so, if you have a look at questions 37 to 48, it's asking you to find or to show that they're inverses, which means that they have to be 1-to-1. So if you try any of those to show that they're all 1-to-1, they will all be 1-to-1, and they will all be easy to deal with, right? And you'll see that they just fall out. When it doesn't, when you hit a glitch like this, it's not 1-to-1. Done. All right. We kind of already did it, right? But what we said was, because I know what a parabola looks like, essentially what I'm using is the horizontal line test up here, right? So a horizontal line test, so a horizontal line is like this. And so a function's 1-to-1 if no horizontal line intersects the graph more than once, right? So any power of 2, 4, 6, blah, 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 any even power won't be 1-to-1. Okay. I want to come back to the inverse function property. The inverse, we denote it as f to the negative 1. So the inverse of f, the inverse of f of x is denoted by f to the negative 1 of x. To find the inverse, and again, I stray a little bit from the notes, and if you stick to the notes, then that's fine. It's just two different ways of doing it. To find the inverse, first we have to make sure that it's 1-to-1. And so steps to finding the inverse, which I'll put on this new page here. Steps to finding the inverse of f of x. Step 1, show that f of x is 1-to-1. So I skipped ahead in the notes on the next page where it outlines how to find the inverse of a 1-to-1 function, because my steps are just slightly different. It depends on what you like. Show that f of x is 1-to-1. Step 2, this is where I straight write y equals f of x. Step 3, now wherever I see a y, I'm going to write x instead, and wherever I see an x, I'm going to write y instead. Question?
Oh, no.
No. Oh, just.
So that's the inverse. The inverse would be x equals f of y then?
Yeah, but then we solve for y to get the inverse. Yeah. So we swap the variables, and then we solve for what we usually solve for, but that's the inverse. So we write y equals f of x, and then swap x's and y's. And then step 4 is solve for y. This will be the inverse of f. This will be f inverse. Let's steal a problem here. If it asks you, or if I ask you to find the inverse, you can assume it's 1-to-1, but I still will probably ask, just like on the practice test, right? The last problem says, show f of x is 1-to-1 before finding the inverse, right? So you're gonna have to do one of these. So let's do it just as if we're writing the test question. So first thing we're gonna do is show that f of x is 1-to-1. Which one do you guys wanna do? Maybe 68 or 70. There's some restrictions on 70. How about 70? Come on. All right. 70. Show f of x is 1-to-1. Remembering that x is only on the interval 0 to 2 inclusive. And so that's kind of my first step. So I've got f of x is the root of 4 minus x squared. So f of a, I'm going to set it equal to f of b. I've got the root of 4 minus a squared, hopefully is equal to 4 minus b squared. So far, so good, right? Because I'm going to square both sides to get rid of, it doesn't matter which square root I'm getting rid of. So I get 4 minus a squared is 4 minus b squared. You don't need to show that you're squaring it. They'll just kind of go away. Or if you wanted to do something like that, either way, 4 minus a squared is 4 minus b squared. I can subtract 4 from both sides. Doesn't really matter which way you're moving, but we get 4 minus a squared minus 4 is negative b squared. 4 minus 4 goes away, so I have negative a squared is equal to negative b squared. Looks promising, right? Divide both sides by -1, or even multiply both sides by -1. I get a squared -1 times negative a squared is b squared. So a squared is b squared. I'm going to take the square root of both sides. square root of a squared is the square root of b squared. Would you look at that? A is equal to b. So therefore, f of x is 1-to-1. Which we're pretty happy about, right? Took a little bit more work, but like I said, it will just fall out, right? And on the test, it will be 1-to-1, right? So it will just kind of come together. You just have to show that it's 1-to-1. So now, step 2 is to write y equals f of x. So what I'm going to do is I'm going to say y equals, and where did we have it here? The square root of 4 minus x squared. Step 3 for me, because I think the notes here, the textbook says write y equals f of x, so we're on the same page, but then they want you to solve this in terms of x, which is fine, but sometimes I find it hard to change gears because we're usually solving for y, right? Y equals this, y equals this. And so that's why I like to swap these, but we're doing the same thing, right? So you could either just solve for x here, right? And have y as your variable, and that's your inverse, or I like to swap my x's and y's. Swap x's and y's. So I get x equals the root 4 minus y squared. Fine. And then step 4 is solve for y. So now I have x is the root of 4 minus y squared. Solving for y, right, I square both sides, so x squared is 4 minus y squared. So I have x squared minus 4 is negative y squared. Bring that negative over, I get negative x squared minus 4 is y squared. And then I can square root that. So I have the square root of negative x squared minus 4, negative on the outside though. You can bring it inside, right? You can simplify in there. You could even rewrite it as 4 minus x squared. Maybe you can't. Negative x squared. Yeah, you can. But I just leave it. Here's where that restriction comes in, right? X is only between 0 and 2, which is why we're safe, right? Because we've got negative something minus 4, something positive minus 4. Let's just make sure X is between, is it 0 and 2? Yeah. So now, what happens if X is 0? I get negative 0 minus 4. That doesn't work.
Wouldn't be plus 4 because you have to put the negative all the way through.
Done. It does work. And you know what? I will rewrite it. Negative x squared plus 4. Better. 0 squared plus 4 is positive, all the way up to 2 squared. But then it's negative, so the negative's on the outside, right? The x is the squared, but so here you have to think of this as one number, and that's why we have to have that restriction on x, right? Because if you had x equals 3, right? 3 squared, 9, but then it's negative 9 plus 4 puts you at a negative number, right? So that's why they have that restriction on there, because otherwise it just wouldn't work out. It wasn't something that we had to deal with. It was just to make it make sense. So this equals y. And so now, therefore, f inverse of x is this function negative x squared plus 4. And out of time, but the inverse function property says that f of f inverse of x equals x, but also that f inverse of f of x also has to equal x. And that's just a fact, right? This is f composed with f inverse. F composed with f inverse of x equals x, but also f inverse composed with f of x equals x. And this is the inverse function property. So here, this is how you can check to make sure that the inverse that you found is actually the inverse of x, because once you find the composition, they should both equal x, no matter the order. Oh, sorry to run you through 2.8. But those domains in 2.7, they're a big deal, so it's good. Any questions? Okay. Yeah. It's just going to be solve this, solve this, solve this, solve this. So here, so see how it says 6 of the following? It'll be, and then 2 of the following. It'll be from these exact questions in this order, unless there's like spacing issues. But usually I try to keep it in the same order that the practice test is in.
And it's all long.
Yeah, yeah. So does that answer? Yeah. Cool. All right. Have a good weekend. Text me, email me, do whatever if you have any questions. All right.